Hello, and welcome to this online lecture. My name is Patty Kokish, and today we're going to be covering topics from Math 200 at Ivy Tech. So we're going to cover Chapter 7, which is the normal probability distribution. I want to point out a couple of people, since I do have people logged on live today. If you have any questions on anything that we're doing, you can go ahead and type them either in the chat or the questions tab of GoToWebinar. And then what will happen at the end of the lecture is any questions that you guys have at that point, I'll go back and answer them. And if you have a particular question about a certain slide, it would be nice if you could write down the slide that you're asking about so that I know exactly where to go in the presentation. All right. So we're going to start with section 7.1, which is the properties of the normal distribution. There are several objectives in this section. The first is to be able to use the uniform probability distribution, then graph a normal curve, state the properties of the normal curve, and explain the role of area in the normal density function. So the first objective, we want to learn how to use the uniform probability distribution. So let's suppose for a minute that the UPS is supposed to deliver a package to your front door, and the arrival time is going to be somewhere between 10 a.m. and 11 a.m. So we're going to let x be a random variable that represents the time from 10 a.m. until the delivery is supposed to take place, which could be 11 a.m. So the delivery could be at 10 a.m., which would be x equals 0, okay? Or it could be maybe at 11 a.m., which would mean that x would equal 60 because that's 60 minutes from 10 a.m. And we're going to do just 1 minute intervals, okay? So it would be x equals 0, 1, 2, 3, all the way up to 60. And we're going to assume that any time in that period from 10 to 11 is going to be equally likely. So that is to say that your package is just as likely to arrive between 10:15 and 10:16 as, say, 10:40 and 10:41, okay? So there isn't a particular time when we're expecting it more than any other time. So the random variable x can be any value in the interval from 0 to 60, okay? And because any two intervals of equal length between 0 and 60 are inclusive, they're going to be equally likely, and the random variable x is going to follow something called a uniform probability distribution. I think we're going to come back and look at what this looks like in just a minute, but that's just kind of an example of what a uniform distribution might be in sort of a real-world scenario. So a probability density function is an equation used to compute probabilities of continuous random variables. So it has to follow a couple of, or satisfy a couple of properties. The total area under the graph of the equation over all possible values has to equal 1. And then the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. So for example, you can't have a negative height. So if we look here, this is kind of the same example we were talking about. The graph below illustrates the properties for the UPS time example. So what we can see here is that we have values of x between 0, so we start at 0 and we go all the way to 60, okay? And we could label some more of these, but this is just a big block from 0 to 60. And then what you'll notice is that for any one probability, we have a probability for any one time interval, like from 0 to 1, or 1 to 2, or 2 to 3, we have a probability of 1 over 60. And what you should notice is that the area of the rectangle is going to equal 1. So if you recall how to find area of rectangle, it's always just length times width. So the length is 60, or we could call this the width, it doesn't really matter. And then the height here, or the width, or whatever you want to call it, is 1 over 60. So when we multiply those two together, we get 1, which is exactly what we want. So because the area of the rectangle is height times width, the width of the rectangle is 60, the height must be 1 over 60. So this is kind of forced to be 1 over 60 because of the fact that the area has to be 1. Values of the random variable x less than or greater than 60 are impossible because we know our package is going to arrive between 10 a.m. and 11 a.m. So the function must be 0 for x less than 0 or greater than 60. So we're not going to have it arrive before 10 a.m. It's not going to arrive after 11 a.m. So all of these probabilities are going to just be 0. So they're considered impossible events. Now, the area under the graph of the density function over an interval represents the probability of observing a value of the random variable in that interval. So if we look here, we've labeled some kind of extra points on our UPS time example. And what we're trying to find is the probability of choosing a time that's between 15 and 30 minutes after the hour. Okay, so I think between 10:15 and 10:30. Okay, now if you look at this, these all have equal probabilities. So what we've done is we've shaded the area from 15 to 30. Okay, and we get this kind of sub-rectangle within our rectangle. And if you think about it, we're going to have 15 little intervals in here. Okay, 15 to 16, 16 to 17, and so on. So this is going to account for 15 out of the 60 total little pieces that you'll have. So that means that the probability is just going to be 15 out of our 60, or 0.25. And if you think about it, any 15-minute time increment that we're going to be talking about, we have a 25% chance of landing in that 15-minute time increment. Because if you think about it, we could have a rectangle from 0 to 15. It's going to be the same size as 15 to 30, 30 to 45, and then 45 to 60. So it's just 1/4 of the whole, or 0.25. Or if you want to think of it as a percentage, it would be 25%. Okay, objective 2 is to be able to graph a normal curve. So let's look at this example here. So relative frequency histograms that are symmetric and bell-shaped are said to have the shape of a normal curve. So if we look at this here, we just have a relative frequency histogram. Our y-axis isn't labeled, but we can assume that it's a relative frequency. It doesn't really matter too much. But when we overlay this bell curve on top of it, this looks pretty good. It looks like it's following this pretty exactly. So this is a good example of something that is said to have the shape of a normal curve. So if a continuous random variable is normally distributed or has a normal probability distribution, then we can say that the relative frequency histogram of the random variable has the shape of a normal curve, which is bell-shaped and symmetric. Now, there are a couple of kind of interesting things about normal curves. The first is that sort of this high point right here that you have, that's going to be mu, which is just your mean, okay, so your average. And then if you kind of notice what happens here, we have these things called inflection points, which you may be familiar with from previous math classes. But basically, that's where the concavity of your graph changes. If you're going to take calculus, you'll see inflection points there as well. But what you'll see is it kind of changes direction from looking like an upside down U to kind of maybe a right side up U, okay? And these inflection points happen at a particular point, at mu minus sigma and mu plus sigma, where this is your standard deviation. And if we look at just a couple of examples here, you can kind of see how bell curves might differ from one another. So if we look at these examples up top, these have the same spread, okay, so the standard deviations are both 1 in each case, so that means that they're spread out the exact same amount. But if you look at the one on the left, this kind of pink reddish one, the mean is 0, okay, so that means that the highest point is at 0. And then the blue one, the one on the right, the mean is at 3. So basically, the blue one is just a shifted version of this pink or red one. But if we look down here, we have the same means, so mu is equal to 0 in both cases, but the standard deviations are different. So if you look at the pink one, the standard deviation is 1. We have a fairly small standard deviation, so that means everything is kind of grouped right in the middle here. But right here, we have a standard deviation of 2, okay, on our blue graph, so that means that everything is spread out just a little bit more. Okay, objective 3 is to be able to state the properties of the normal curve. So there are several things that you should know. It's symmetric around the mean, which is mu. Because the mean is the same as the median, which is the same as the mode, the curve has a single peak, and that highest point occurs at x equals mu, okay, which would also be the median and the mode. And then we talked about inflection points, mu minus sigma, and whoops, this should be mu plus sigma, sorry about that. The area under the curve is 1, just kind of like we talked about with the uniform density. And then the area under the curve to the right of mu is going to be equal to the area under the curve to the left of mu, which is just 1/2. So if you think about that, that's just kind of a subsequent thing based on properties 1 and 4. So we know it's symmetric around the mean, and then we know also that the mean is in the middle, and then we also know that the area around the curve is 1. So if you can imagine kind of your normal curve here, we have mean in the middle, if we take the right-hand side and flip it across the mean, it should be pretty much the same as the left. So that means that the area to the right is going to be the same as the area to the left. So they're both going to just be 1/2 or 50%. As x increases without bound, meaning it gets larger and larger, the graph approaches but never reaches the horizontal axis. And then as x decreases without bound, meaning it gets more and more negative, the graph again approaches but never reaches the horizontal axis. And then also the empirical rule, which we've talked about before, that was also called, you may have remember it as 68, 95, 99.7 rule. So what that tells us is that approximately 68% of the area under the normal curve is between mu minus sigma and mu plus sigma. Approximately 95% is between mu minus 2 sigma and mu plus 2 sigma. And 99.7 is between mu minus 3 sigma and mu plus 3 sigma. So we have 68% of our observations within 1 standard deviation of our mean, 95% of our observations within 2 standard deviations of our mean, and 99.7% of the observations between 3 standard deviations of our mean in either direction. So if we look at this right here, this is kind of a visual representation of that empirical rule. So we have our mean in the middle, and then if we go to the left 1 standard deviation and to the right 1 standard deviation, we end up with this blue area here, okay? And this is going to be 68% of our observations. Okay, now you don't need to memorize the 34, 34, 13.5. I'm going to walk you through kind of quickly, but I'm going to walk you through how you could get those numbers on your own just by knowing 68, 95, and 99.7. Now, if it's not making sense to you, I would recommend that you go ahead and memorize these so that you get these types of questions correct. But really all you need to know are these 3 numbers. So if you think about how they got this 34, we know that the blue part is 68%, and we also know that we're symmetric around our mean. So that means that this left-hand piece and this right-hand piece are both the same. So all we have to do is take our 68% and divide it by 2, and that gives us our 34 and our 34. Together they create the 68. Now, if we add in kind of this tan piece on the side, we know that this entire thing, the tan piece plus the blue piece, all of this right here, that's going to be 95%. So if you think about where this 13.5 came from, we know that the tan plus the blue is going to be 95, but then if we take away the blue pieces, that would be 95 minus 68, okay, and that would give us 27. And then what we would do is we'd take our 27 that we have left over. We know that between these 2 tan pieces, we're going to have 27% of our observations. So we take our 27 and divide it by 2, and we end up with our 13.5 and our 13.5. Now, in order to get these green pieces, we know that from this green area to this green area, okay, so the green, the tan, the blue, the entire thing, that gives us 99.7%. Okay, so if you think about it, if we take the 99.7%, which is this entire thing, and we take away the tan and we take away the blue, so we take all of it away, so that would mean that we'd take our 99.7% and we'd subtract our 95%, so we'd be left with 4.7%. And then we divide it amongst the 2, so we take our 4.7 divided by 2, that gives us 2.35 in this left-hand side green part and 2.35% in the right-hand green part. And then the other thing to kind of keep in mind, I'm looking, it's not on the next slide, so I just want to talk about it really quickly, is that the entire thing, all the way on the left to infinity and to the right on infinity, or to infinity, it's going to be 100%. So that means to the left of this green part, we have 0.15%, and to the right of this green part, we have 0.15%. So really, really small, but it will still mess up your answers if you don't include it. Okay, objective 4 is to explain the role of area in the normal density function. So the data on the next slide represents the heights in inches of a random sample of 52-year-old males. Draw a histogram of the data using a lower class limit of the first class equal to 31.5 and a class width of 1. Okay, so we're going to use 31.5 as our first lower class limit and a class width of 1. And then we want to know if the variable height of 2-year-old males is normally distributed. So here's our raw data here. Now you should never have to create the histograms by hand. You want to probably use these or do these using StatCrunch. So hopefully you know that when you're doing your homework, when you're given data like this, if you kind of mouse over the top right-hand side of the data, it has sort of like, it looks like a little screen. And if you click on that, it comes up with some options, and you do open in StatCrunch. And then what it'll do is it'll open StatCrunch, which is a great little statistical tool that is kind of integrated into your textbook. And you'll open it in StatCrunch. And then you can go ahead and draw histograms, you can find mean, median, mode, standard deviation, you can conduct tests, all kinds of really cool things. So this particular histogram, I think it looks like it was created to me in Minitab, which is kind of a similar statistical tool to StatCrunch, but you could definitely do it in StatCrunch. And you'll see that we have a lower class limit for our first class of 31.5, and the width is 1. So each one is 1 unit wide. And then we have the percents listed over here. We could also list these as decimal probabilities, doesn't really matter. And what you'll see is that heights of 2-year-old males in inches, this looks pretty normal, okay? And if we actually stick a nice little normal curve over it, it follows this quite well, okay? So this looks pretty normal. Later in the class, we will do actual tests to determine if something is normally distributed. I think that is covered in this class. I'm not 100% sure. There are actual statistical tests, though, that we can do to tell. But normally our eyes are pretty good, and this looks like it fits our data pretty well. Okay, so area under a normal curve. Let's suppose that a random variable x is normally distributed with mean mu and standard deviation sigma. The area under the normal curve for any interval of the values of the random variable x represents either the proportion of the population with the characteristic described by the interval of values, or the probability that a randomly selected individual from the population will have the characteristic described by the interval of values. So this is just kind of useful in interpretations. So let's look at this example here. The weights of giraffes are approximately normally distributed with a mean mu of 2,200 pounds and a standard deviation sigma of 200 pounds. So we want to draw a normal curve with the parameters labeled, shade an area, and then go ahead and interpret a result. And what's given here is that we're told what the area is going to be. It says, suppose that the area under the normal curve to the left of 2,100 pounds is 0.3085. We'll learn in just a few minutes how to actually figure that out, okay? But for right now, it's given to us. So if we look at this right here, we have our mean of 2,200, that's smack dab in the middle, and then we've drawn our nice little normal curve, which has a standard deviation of 200. And then we've also shaded to the left of 2,100. And it was already told to us that this area, this kind of purpley blue shaded area, is 0.3085 or 30.85% of the total, okay? So if we wanted to interpret this, we could say that the proportion of giraffes whose weight is less than 2,100 pounds is 0.3085. Or we could say that the probability that a randomly selected giraffe weighs less than 2,100 pounds is 0.3085. Or I also think it'd be fine to use it as a percentage. So we could say that the probability is 30.85%. Okay, we're going to move on to section 7.2, which talks about applications of the normal distribution. So the objectives in this section are just to find and interpret the area under a normal curve, find the value of a normal random variable. So let's start with objective 1, which is finding and interpreting the area under a normal curve. So at this point, if you don't have your textbook out, you probably want to pull up at least the table in the back, okay? And this is in the appendix. Let me find the number for you so that you can find it. It's table 5 in the back of your book. It's just the normal distribution table. If you have the actual physical textbook, it's A11. But if you have the ebook, you might want to open that up as well and then go to the appendix, and it's on A11, but it's table 5, the standard normal distribution, and that goes from A11 to A12. So we'll be using both of those pages, and you probably want to pop that open at this point because we're going to be using it. Okay, so I think we've talked about z-scores before, so you should be familiar with this, but let's just go through them one more time, and then that's what we're going to use in order to find some areas under our curve. So let's suppose that a random variable x is normally distributed with a mean of mu and a standard deviation of sigma. Okay, this is pretty typical. So the random variable z equals, we take x, which is kind of like our data item, minus our mean, and divide by our standard deviation. That's going to be normally distributed with a mean of 0 and a standard deviation of 1. So the random variable z is actually said to have the standard normal distribution. So if we look at this here, we have our standard normal curve. These are going to be kind of what our z-scores are going to look like. Mean of 0, standard deviation of 1. So if you look at 1 and -1, we have inflection points there. And then z is maybe what we're interested in. Maybe we're finding the area to the left of z. So the table gives the area under the standard normal curve for values to the left of a specified z-score z, as shown in the figure. So if you look at the actual table on page A11, this again is table 5 in your book, all the way back at the appendix at the end of the textbook. And if you look where it says table 5, it says standard normal distribution right up below that, but above it there's a picture, okay, and that kind of depicts exactly what is shown on this slide, which is that all of the values in the table give you the area to the left of z, okay? So if that's not what you're given in the context of the problem, then you have to do a little bit more thinking in order to get that. So let's look at this example here. So IQ scores, this is kind of a nice thing to use with normal distribution. IQ scores can be modeled by a normal distribution where the mean is mu and the standard deviation is 15. Okay. Oh, sorry. Mean is mu, which is 100, and standard deviation is 15. So an individual whose IQ score is 120 is 1.33 standard deviations above the mean. And in order for us to get that, we take the 120, which is what we're kind of interested in. Okay, that's what I'd like to call it. What we're interested in, the 120, minus the mean, which would give us 20, and then divide by 15, and you get 1.33. Anytime you have a positive z-score, the way that you can know if you got it right, that you subtracted in the right order, is if you end up with a positive z-score, that means you're above the mean. Negative z-scores signify that you have something that's below the mean. And if you think about an IQ score of 120, that's definitely above the mean, so we should have a positive z-score, which in this case we do. So what I'd like you to do is look at your table, okay? And what you're going to do is you're going to find the 1.33, which is our z-score, on the actual table, okay? So if you look for the 1.3 on the left-hand side, and if you're on page A11, you'll notice all of the numbers there are negative. You're going to have to flip your page to page A12 so that you have the positive z values. So you're going to look for 1.3 on the left-hand side where it says z. It's bolded there. And once you find 1.3, what you're doing is you're looking for this next digit here. So the 1.3, if you look on the screen, is this 1.3 right here. And then along the top, you also need to find this second digit. Okay, so the digit that's in the hundredths place. So we look for 1.3 and then we go over to where it has 0.03. And what you'll find is that the intersection of those two, just as it's shown on your slide, is 0.9082. So if we look at how this actually works, if we look at our picture, and I always suggest drawing pictures when you're doing normal distribution z-score problems, okay, 100 goes smack dab in the middle, okay, we have some standard deviations labeled 115, 85. We don't have to label those, but kind of helps us be on the right scale. 120 is the one that we're interested in, okay, so the 120 goes right here, and then we know that everything to the left of the 120 is 0.9082. Okay, so about 90.82% of scores are going to be less than 120. But if we want the area to the right of 120, which is kind of this tan shaded part, all we have to do is take 1, because that's the entire area. If you remember all the way from -infinity to infinity, or whatever range of values make sense, okay, that whole thing is going to be 1, okay? So all we have to do is take 1 minus our 0.9082, and we're left with 0.0918. So there's no sentence given, but if we wanted to kind of write a sentence, we would say that the probability of selecting a random individual with an IQ over 120 is going to be about 9.18%. Okay, so if we look at the areas under the standard normal curve, I'm not going to go through this again because these are the same as the 68, 95, 99.7 rule. Okay, these are the same probabilities or proportions given here. So let's say that we want to find the area under the normal curve to the left of z equals negative 0.38. So what you're going to do if you're on page A12 that has all of your positive z-scores, you've got to flip back one page to find the negative z-scores. And since we know negative 0.38, that means we're going to go down to z equals negative 0.3 and then over to the 0.08, and we end up with 0.3520. Now, since we're just interested in the area to the left, that means that the number on our table, that's just our answer. So our answer is just 0.3520. If we wanted the area to the right, that means we would have to do 1 minus the table value. So again, to state it kind of more clearly, if we're finding area to the left, all we do is we find our z-score and we look it up on our table. If we're finding area to the right, we find our z-score, we look it up on the table, and then we do 1 minus that value. Okay, so if you look here, this is kind of the same thing, just in different words. Area under the normal curve to the right of z naught is equal to 1 minus area to the left. Okay, so let's say we want to find the area under the normal curve to the right of z equals 1.25. Got to flip our page again because we need positive z-scores. So we want to look for 1.2 on our table, and then go over to 5. Okay, so 1.2 and then 0.05 looks like 0.8944. So in order to find the area, we have to do 1 minus 0.8944, and we get 0.1056. So that means the area to the right of 1.25, or z-score of 1.25, is going to be 0.1056, or about a 10.56% chance. Okay, we can also find areas between. Okay, so far we've done less than, more than. We can also be finding two z-scores and then help to calculate the area between. Now, this is not too difficult to do. Okay, all you have to do is find the area of one and subtract it from the area of the other. Okay, and we're always doing areas of lefts. So if we want z equals 2.94, since we're already on the positive table, we go ahead and look at 2.94. And we get 0.9984 when you look that one up. And then we subtract the area to the left of negative 1.02, a z-score of negative 1.02. So we go down to negative 1.0 and then over to 0.02, and we get 0.1539. And then we just subtract those values. So we get 0.8445, or 84.45% of observations are going to be between z-scores of negative 1.02 and 2.94. Okay, so here's a nice little summary. We're going to go through 3 slides that have kind of the 3 different approaches and solutions. So if we want to find the area to the left of x, we just shade to the left. We find a z-score and look it up on the table, and that's it. You can also use technology to find the area. So if you have a graphing calculator, it will do that as well. StatCrunch will also do this. If you want area to the right, again, you convert the value to a z-score, use the table to find the area, and then do 1 minus that table value. Or again, you can use technology. If you want area between, then you calculate both z-scores. You use table 5 to find the area to the left of z1 and to the left of z2, and then you just find the difference between the two. And you always want to subtract in a way so that you get a positive answer. It wouldn't make sense to have a negative area, so you want to make sure you take the largest number minus the smallest number. Okay, objective 2 is to find the value of a normal random variable. So the procedure for finding the value of a normal random variable is to just draw a normal curve and shade the area corresponding to the proportion, probability, or percentile. Use table 5 to find the z-score that corresponds, and then obtain the normal value from the formula x equals mu plus z times sigma. So if we look at this example here, The combined score on a GRE is normally distributed with a mean of 1,049 and a standard deviation of 189. So we want to know what is the score of a student whose percentile rank is at the 85th percentile. So what we actually need to do is, instead of looking up the z-score on our table, we actually need to look for the 85th percentile in the actual body of the table. So if you start looking in the actual body of the table, what we want to do is we want to find the number that's closest to 0.85. Okay, so if you're looking in your table, you're looking in the actual body of the table for 0.85. And if you look for it, I think you should find it at 1.0 and then all the way over to 4. You get 0.8508. That's the closest number to 0.85, so we're going to use that one. So that means that a z-score of 1.04 corresponds with the 85th percentile. So all we have to do is we have to take our mean, which is 1,049, and add 1.04, which is our z-score, multiplied by the standard deviation, which is 189. And we get 1246. So in order to interpret this, we would say that a person who scores a 1,246 on the GRE would rank in the 85th percentile, meaning that he or she would score higher than 85% of all people. Only 15% would score higher than him or her. So you're always going to take mu plus your z-score times your sigma. Sometimes your z-score will be negative if you're talking about something that's less than 0.5, okay? And if you're given the percentile, you have to actually look for the percentile in the body of the table and then find the z-score from that. Okay, so it is known that the length of a certain steel rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45 centimeters. So let's suppose the manufacturer wants to accept 90% of all rods manufactured. Determine the length of the rods that make up the middle 90%. So if we look at this one's a little more confusing because we're trying to find the middle. So if you look at the example we have here, this tan part in this middle, this is going to be our 90%, okay? And then we're going to be left with 5% on the right and 5% on the left. So what we need to do is we need to find these values that make it so that we have 5% on the left and 5% on the right. And if you actually look at these are kind of typical z-score values. You might get used to these, all right? But if you look at them, let's see here. We're looking for 0.05 in our actual table. And if you go to negative 1.6, you'll find that the 0.05 is smack dab in the middle between negative 1.64 and negative 1.65. So it's negative 1.645. Now, since we know that our distribution is symmetric, if this is the negative one, and we want the area to the right of this one to be the same, we're just going to have the same positive z-score over here. So that means that we have z-scores between, or sorry, we have a lower bound z-score of negative 1.645 and an upper bound of positive 1.645. So again, we take our mean and we add our z-score times our standard deviation. So we take our mean of 100, which was, I can't remember now the situation we were talking about. Oh, the steel rod. So we take our 100 and we add our z-score, the negative 1.645, multiplied by the standard deviation of our steel rod, and we get 99.26 centimeters. And then we take our second z-score, and again we add it, and we get 100.74 centimeters. So you'll notice that 100.74 and 99.26, smack dab in the middle of those, is the actual mean, which is 100. So the interpretation of this is that the length of steel rods that make up the middle 90% of all steel rods manufactured would have lengths between 99.26 centimeters and 100.74 centimeters. So that might be useful when you're talking about how to reject or accept maybe a shipment of steel rods. So if you have a lot of steel rods that are kind of outside of this middle 90%, then maybe you would be rejecting the shipment. Now, there are actual rules in place for that, but that is kind of one way that that this could be used sort of in a real life scenario. Okay, so the notation Z alpha, or we can read it as Z sub alpha, is the Z score such that the area under the standard normal curve to the right of Z sub alpha is alpha. Okay, so if you look at here, we have our Z scores along the bottom. This we're just going to call Z sub alpha, and the area over here is going to be alpha. Okay, so section 7.3 is all about assessing normality, okay? And thankfully, we're not going to do too much in this section. We're going to use technology to help us assess normality, all right? So we're going to use normal probability plots in order to do this. Now, what a normal probability plot does is it takes the observed data and it plots it versus the normal scores. Now, normal scores are kind of the expected z-scores of the data value if the distribution of the random variable is normal. So the expected z-score of an observed value is going to depend on the number of observations in the actual data set. So if you want to draw a normal probability plot, we're going to go through the steps so you understand how these are created. But when you're actually creating these, I want you to definitely use StatCrunch in order to do this. Okay, so the first step is to arrange the data in ascending order and then compute all of these expected proportions. Okay, you're going to take I. I is going to be the index, meaning it's the position of the data value in the ordered list. Okay, so the first data value, it's going to be 1. And then n is going to be the number of observations. So you take the index and you subtract 0.375, and then you divide that by the number of observations plus 0.25. And the expected proportion of the observations less than or equal to the ith data point is going to be f. And then you find all of the z-scores corresponding to that, and you plot the observed values on the horizontal axis and the corresponding expected z-scores on the vertical axis. So the whole idea behind finding the expected z-score is that if the data comes from a normally distributed population, we would be able to predict the area to the left of each of the data values. The value of f sub I represents the area that's expected left of the ith observation when the data comes from a normal distribution. So for example, f sub 1 is going to be the expected area to the left of the smallest data value. F sub 2 is going to be the expected area to the left of the second smallest value, and so on. So if sample data is taken from a population that is normally distributed, then this normal probability plot that we're creating of the actual values versus the expected z-scores is going to be approximately linear. So we're going to be content in reading normal probability plots that are constructed using Minitab. You could also, I believe, do this using StatCrunch. Okay, so if you look at this example here, this is an example that pops up a lot in this class. The following data represents the time between eruptions in seconds for a random sample of 15 eruptions at the Old Faithful geyser in California. And then we want to know if there's any reason to believe that the time between eruptions is normally distributed. So they did all of kind of the fancy work for us, and we created this normal probability plot. The blue bands are kind of what you want to look at. But if you look here, we have this observation that is outside of the blue band. Okay, that immediately should tell us that we do not have something that's normally distributed. Okay, so the random variable time between eruptions is likely not normal. Okay, now this is 95% confidence interval, these blue bands. So this isn't, let's say, perfect, but it's pretty good. And what we're going to use it for is just determining right now if something looks normal or not. So if you have points that are outside of the blue bands, then you're going to say, no, they're likely not normal. And if we actually look at a box plot of time, hopefully you recall looking at box plots before, this definitely is not normal. You have kind of this tail here that's longer than this tail, and then you have definitely a very low outlier down there. Okay, let's look at this one here. So suppose that 17 randomly selected workers at a detergent factory were tested for exposure to an enzyme by measuring the ratio of forced expiratory volume and vital capacity. Hopefully I read those correctly. Is it reasonable to conclude that FEV and VC, the ratio, is going to be normally distributed? So we have some values here. Again, we're going to use Minitab, StatCrunch to kind of create our normal probability plot. And you'll see that this is approximately linear, okay, and we don't have any values that are outside of our bands. So it is reasonable for us to believe that it is normally distributed. Okay, section 7.4, I have to say, is probably the trickiest of the sections. Okay, this is probably the most difficult for students and probably takes the most time to really understand, but it is an important section. Okay, so I want to go through it. What we're going to do is we're going to approximate binomial probabilities using the normal distribution. Okay, only one objective, which is good news. So I want to kind of give you guys a little refresher first on the criteria for a binomial probability experiment. So this was from the previous chapter, chapter 6. So if you're stuck on chapter 6 still, I would make sure that you go back and understand that really well before starting this, because you have to understand what a binomial probability experiment is first. All right. So an experiment is said to be a binomial experiment if all of the following are true. The experiment is going to be performed n independent times. Each repetition is called a trial, okay? And independence means that the outcome of one trial has no effect on the outcome of the other. And then for each trial, there are two mutually exclusive outcomes, either success or failure. And then thirdly, the probability of success P is the same for each trial of the experiment. So those are the criteria that need to be met in order to have a binomial probability experiment. So for a fixed P, as the number of trials n in a probability experiment increases, so meaning we have more and more observations, then the probability distribution of the random variable x becomes more nearly symmetric and bell-shaped. So as a rule of thumb, we say that if n, which is our number of observations, times p, which is our probability, times 1 minus p is at least 10, okay, so if it's greater than or equal to 10, then the probability distribution is going to be approximately symmetric and bell-shaped. So this is the actual statement of the normal approximation to the binomial. So if n times p times 1 minus p is at least 10, the binomial random variable x is approximately normally distributed with a mean of n times p. Okay, so you take your number of observations times your probability of success, and then the standard deviation is given as the square root of n times p times 1 minus p. Okay, so if we look at this example right here, we have a binomial histogram. N is equal to 40, p is equal to 0.5. Okay, so we have 20 right in the middle because that would be half of 40, or 0.5 times 40. Excuse me. And let's say we wanted to approximate the probability that x is equal to 18. If you look at this, if you look on either side of 18, it's going to be approximately equal to the probability that x is between 17.5, which is going to be this right here, and 18.5, okay? Because if you look here, we have a little piece that is not included, okay, in our shading, and then we have a little extra piece that is included. These are really, really close to one another, okay? So this is a pretty good approximation. If we look at this example here, if we wanted the probability that x is less than or equal to 18, if we look at it, that means we would want 18, 17, 16, 15, all the way down here, okay? So what we would do is we'd actually add 0.5 to this, okay, so that we end up with this extra little piece. So now we have this extra shaded piece, and that helps us approximate because we have all of these tiny blue pieces on the outside that are not accounted for. So each one of them has kind of an extra green piece inside now. So this blue piece corresponds with this little green piece that's extra inside. So this is a pretty good approximation. So if we have a less than or equal to question, we add 0.5. So if we look at the actual rules that we have, and let me point you in your textbook to where these are because this is it's a pretty good graphic that they show you. It's chapter 7, section 4. It's page 358. So if you have access to your ebook, it's in section 7.4, page 358. So you probably want to navigate there. Okay, so the exact probability using binomial, if you want to find that, so if you just want to find the probability of A happening, what you're going to do is you're going to subtract 0.5 from A, you're going to add 0.5 from A, and then you're going to find the probability that x is between those two numbers. Okay, so that's kind of represented by this sort of bar right here. Now, next, if you want the probability that x is less than or equal to a, you have to add 0.5. Okay, that kind of gets it's called a correction for continuity, okay, because we're using a continuous distribution to approximate something that's discrete. So we add 0.5. and then we find the probability that this is less than. If we wanted greater than, then we still have to use the same continuity correction. We subtract 0.5 though, okay, and that's shown on your chart on page 358 as well. And then if you want the probability that x is between A and B, you subtract 0.5 from A and add 0.5 to B, and then find the probability between. So we're going to look at a couple of examples. I would highly recommend that you read your textbook for this section, okay, because it is quite difficult. You could also probably find some very useful videos on Khan Academy over this, okay, but I would definitely actually read your textbook. I would always read your textbook, but particularly for this section so that you can see a couple of extra examples. So according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. Okay, so that's what they say. And then what we're going to do is we're going to take a random sample of 400 car-owning households. So we're going to randomly select 400 car-owning households, and we want to know what is the probability that fewer than 150 have 3 or more cars out of our 400. Okay, so what we need to do is first we need to verify that our conditions are met. So we need to take n times p times 1 minus p, and we need to make sure that it's at least 10. So we have 400, that's our sample size, times our probability, which is 0.35. That's our probability of success, okay? And then we multiply that by 1 minus 0.35, and we get 91, which is obviously much larger than 10. So that means that that assumption is met, okay? We go ahead and calculate the mean. Mean is n times p. Okay, so we take our 400 times our 0.35 and we get 140. And what that actually means is that in a bunch of random samples of 400 car-owning households, we should end up with a mean of about 140 out of those 400 that have 3 or more cars, based on the percentage that Experian Automotive is telling us. Standard deviation is going to be the square root of 400 times 0.35 times 1 minus 0.35, which is going to be 9.54. So that's our standard deviation. So if we want the probability that x is less than 150, what you need to remember is that this is a discrete distribution. So I can't have, for example, 150.2 households that have 3 or more cars. I either have 150, I either have 149, 148, or so on. So if I want x to be less than 150, I don't want to include 150. So what I actually want is I want the probability that x is less than or equal to 149. Okay, when you're setting these up, you always need to have less than or equal to, okay, or greater than or equal to. Okay, so you need to first rewrite your question so that it has an equals to portion as part of the inequality. So probability that x is less than 150 is equivalent to saying the probability that x is less than or equal to 149. Because, for example, we can't have 149 and a half cars. Now, what we do is we look on our chart on page 358, and what we're trying to do is we're trying to find a less than probability. So if you look kind of at the second row down, what we need to do is we need to add 0.5 to our value. So I need to find the probability that x is less than or equal to 149.5. Okay, now we know we can't have 149.5, but what we're doing is we're using the normal distribution, which is a continuous distribution, to approximate something that is discrete, okay? So this, again, is called the continuity correction, okay? So we add our 0.5 and we get 149.5, and then I just need to calculate a z-score. So we need to know that z-score is what we're interested in, which is our 149.5, minus our mean, which is 140, divide by 9.54, and go ahead and do that. So take out your calculator, take your 149.5. I'm just getting mine out. Sorry, hold on one second. So I take my 149.5, subtract my 140, divide by 9.54, and I get 0.9958. Okay, so I want to go to my z table all the way back in the back of my book at my appendix, table 5. Okay, and what I'm looking for is a z-score. I don't want to look for 0.9958 because that's going to round up actually to 1.0. So if I look at 1.0 as my z-score, so I go down to 1.0, just over to 0.00, I get 0.8413, which is exactly how they got this value right here. And again, you could use technology to find that value as well. Okay, I think this is the final example, but let's look at this right here. In a random sample of 400 car-owning households, what is the probability that at least 160 have 3 or more cars? So I want to find the probability that X is greater than or equal to 160. So if you look at your table, when we're finding greater than or equal to probabilities, you have to actually subtract zero point 0.5. So what I'm finding is the probability that X is greater than or equal to 159.5. Once you have it set up like this, you need to go ahead and calculate your z-score. So you take what you're interested in, which is your 159.5, you subtract your mean, which is 140, which we found on the previous slide, divide by the standard deviation, and I'll give you guys a minute to get that. I'm going to get it as well. So I take my 159.5, subtract my 140, divide by 9.54, and I get 2.044. Okay, so what I'm going to do is I'm going to look on my table. I'm going to find z equals 2.04, and I get 0.9793 when I look that up. But if you guys recall from the previous section, when you're finding greater than probabilities, you look the value up on the table and then you always do 1 minus that value. So in your calculator, if you take 1 minus your table value, which is going to be 1 minus 0.9793, you're going to get the 0.0207 that they have right here.